Okay, let's get started. Kevin, for your information, we'll start the Go section. Hi, everyone. My name is Yuan, and this is the 2024 and 2025 USACO season January USACO competition Go level live solution. And today our lecturer is Yibo. He's the past USACO finalist, and also he entered the ACM ICPC with final. Yeah, so at the very beginning, as some of you may not know XCAM, we will quickly play a video.
Computer science and artificial intelligence are tools that will change the future. XCamp Academy is a community dedicated to inspiring and cultivating the next generation of computer science and artificial intelligence talent. XCamp Academy was founded in August 2017 in Silicon Valley by two Google software engineers. The name XCamp was inspired by the variable X, which represents unlimited opportunities. XCamp's curriculum system and training methodology is inherited from Mr. Xian Yongxu, a Chinese diamond-level international gold medal coach. Our staff here in the US is mostly composed of senior software engineers from tech companies in Silicon Valley and prestigious CS students from top universities. In addition, we have strong support from international and domestic competition winners in our coach team. From beginner-level Python to classic C++ courses and competition honors courses, XCamp's curriculum is designed for students of all different levels. By participating in team-based competitions and facilitating frequent group study sessions, XCamp also fosters an environment of collaboration to build each student's confidence in their ability to code. As of mid-2024, more than 300 XCamp students have reached the USACO Silver Division and above, including 60 in the Platinum Division, and 27 were selected in the US and Canada national camps, out of which 15 were fresh in the 2024 season and 2 were selected for the US national team. In renowned high school contests, Stanford's Protocol and UC Berkeley's Calico, and other prestigious US programming competitions, such as the Harvard Programming Invitational, Teams Code, and Lexington Informatics Tournament, XCamp students perform well, and we encourage students from being participants to problem writers and organizers. Our students received 13 MIT offers and many more from Stanford and UC Berkeley, thrilling us all. Here at XCamp, we believe that children have unlimited potential and can change the world through coding.
Okay, yeah, thanks for watching the video. XCamp has been one of the most famous institutes specialized in USACO, especially for those of you who are here who want to listen to the Go section. We have one of the most successful program, the Grandmaster program in the US to help you with USACO. In the past, we have more than 300 students entered the silver and above, and more than 60 entered platinum. 27 USACO finalists, one EGOI gold medal, one EGOI silver medal, and one IOI gold medal. Last year, Brian Sher got the third place in the IOI at Egypt. We hope to help you to achieve the same results as long as you put enough effort. And to help you, we have different programs. The first one is the on-site camp. And today's lecture, Yibo has been teaching XCamp for both camp style classes and also weekend class as well. And during those on-site camp, it will be very helpful for you to really get focused whole day working on problem solving. And the most important thing, again, is not about learning new knowledge. It's more about gaining more muscle memory and get the momentum in competition over time. And second thing is the year-round weekend class. We use these classes to help you to build up the knowledge foundations. And you can also get the contact experience with the mock test class as well. Note that you can also use the online USACO past problems. Those problems are useful too, but some of them could be stale. Some of them could be old and easier than the current level. And you also have if you got selected into the Grandmaster classes at XCamp, that means you are probably one of the few that a coach approved. And if you want to shoot for USACO Gold, planning level or want to enter the camp, which is pretty much is the same as the finalist, or win the IOI gold medal, then you can try to reach out for the grandmaster class. We are looking for students with enough knowledge foundation, but the most important thing is the right momentum, the right commitment, and the good planning for your schedule so that you can invest enough bandwidth into USACO. And lastly, there's a APCS class preparation class for you as well. Okay, that's all, and I will hand it off to Yibo. And Yibo is one of the most popular and one of the favorite teachers at this camp. And now I will turn to Yibo. Yibo, while you do the screen share.
Yeah, sure. Wait, could you leave it on this for a second and then I'll screen share?
Okay, sure.
Okay, so for our 3 problems this time, we had median heaps. Here, our main knowledge foundation needed is dynamic programming, of course. It's also nice to know about heaps, although not strictly necessary. And then the main thing to like do the speed up was doing offline queries and knowing amortized runtime analysis. And these topics are all covered in 302 for heaps, 401 for extensive DP practice, and of course 602P and 602H, which is just like the general like gold training classes. For reachable pairs, this problem we needed to use like DSUs and again offline query. And the classes associated with that is 500 for DSU and 602P, 602H. And then finally, we have photo op. Here, technically, we don't need that much knowledge for this problem. We just need like sets, and we need to do sufficient casework to cover all the cases. All right, and the XCamp courses for this is 400, 500, 602P, and 602H. All right. Yeah, let's jump right into the first problem here. Okay, so for median heaps, essentially for this problem, we are given a heap structure, which means we have a complete binary, or we have a complete binary tree. And then generally, so what this means is every layer of your binary tree is like full, except for your last layer. It doesn't have to be full. You can have some like a partial layer, but all the nodes should be as left as possible. So for example, this would be a valid heap structure. This would not be a valid heap. But if you move this node here, then that's a valid heap again. And then initially they have some values. So I guess we can use the values they have here. So initially this holds 10. This holds 30, 40. And the nodes are labeled like this. Oh, okay. Cool. And what we want to do is we want to change some of these nodes and minimize the cost such that after we run this like median heap algorithm, the top node will have the desired element. And so how this algorithm works is we're going to go to each node, starting from the largest one down to the smallest one in number. And then each time you're going to look at the current node and you're going to look at the 2 children nodes. And you're going to put the median element in, you're going to swap the median element into here. So for example, if you have like a 10 here, a 20 here, and a 30 here, what would happen is you would swap these 2 elements, and the 20 would now go here and 10 would go here. Okay. And so yeah, for each of our queries, we need to output the minimum cost to get the top node to be the exact value, target value M. So let's first think about how we can do this for one singular query. So given a fixed value of M, one nice greedy observation we can note is that if you ever change a value, it's obviously optimal to change it to be M. So for example, if M is equal to 55, and then let's just say I want to change this 50 to something, well, why not just change it to 55, right? Because if you change it to 55, that's definitely going to be just as good, if not better, than changing it to any other value. Okay, and then one way we can think about this is with a DP approach. And here's a initial state we can try. So our state is going to be what's the minimum cost to get the element at node to be one of three things. It's either going to be less than or equal to m, or it's going to be equal to m, or it's going to be greater than or equal to m. And let's start with the leaf case. This is the easiest case. So you can just look at the leaf node. And then if it's already less than or equal to m, which in this case it is, then your cost to get this leaf node to be equal or less than or equal to m is simply 0, right? So we can say our DP here is 0. What's the cost to make this equal to m? Well, the cost to change this node is equal to 10. So we'll just put 10 here. And the cost to get this to be greater than or equal to m, again, it'd be 10 because, yeah, so we can either leave this node as 50, or we can change it for a cost of 10 to be 55. And that's how we get our initial DP calculations for this node. Now let's go ahead and do this for some other nodes. So for this like 40, the calculation is very similar, right? So it costs 0 to leave it as 40, which means it's already less than or equal to m, 55 in this case. Or again, we can change it. And for this node, it costs 1 to change. So just put 1 here. Cool. And now let's take a look at a non-trivial case. So this node here. What's the minimum cost to make this have some value less than or equal to m, or equal to m, or greater than or equal to m? Well, we can just think about all the different combinations of things we can do. So let's say for the first case, let's just leave everything as is. So if you leave this 30 as is, leave the 50 as is, and leave the 40 as is, then your final result here is going to be less than or equal to m. So right off the bat, we know the cost to make this have some value less than or equal to m is already 0. Okay, so let's think about what's the cost to get it to be exactly equal to m. Well, there's only a few ways to do this. So what we know is one of these three values needs to be exactly m, one of these three values needs to be less than or equal to m, and one of these three values needs to be greater than or equal to m. So we can just go through all the combinations or like all the ways to do that and find the way that's the cheapest. Yeah, so like for your code, you can just enumerate out all the ways. So for example, if I make this one less than or equal to m, that costs me 0. If I make this one equal to m, that costs me 1. And if I make this one greater than or equal to m, that's going to cost me 100. So the total cost, if I make this less than or equal to, make this equal to, and make this greater than or equal to, is 101. And that's one possibility. But then you also want to try the other possibilities. So, okay, instead, what if I made it so that this node is less than or equal to? That costs 0. And then I make this node greater than or equal to, and I make this node equal to. And that gives us a total cost of 11 to do so. I believe that's the optimal one. Cool. And then finally, if we want to have some value greater than or equal to m at this node, then again, we can just go through all the ways to assign things. And in this case, the optimal thing to do would be you leave this value as is, and then you make this greater than or equal to m, and you make this greater than or equal to m. So then again, your cost is 11. Cool. And we can essentially do this all the way up. And that gives us well, let's quickly analyze our runtime per query. So our number of states is the number of nodes there are. So this is just n, and then times 3. And then in terms of transitions, so if you're at a leaf node, the transition is really simple. There's only like 3 things to look at. But if you're at a non-leaf node, then your number of transitions is like at 3 to the power of 3. So for each node, we can have at most 3 to the power of 3 transitions because like you basically assign your current node to be less than equal to or greater than equal to, and then you do the same thing for your left node and your right child node. Yeah, so our overall runtime would just be, I guess, technically O of n per query. And then if you multiply this by Q to solve this for every single query, we get a total runtime of O of n times Q. And this works for the first two subtasks. Yeah. Okay. And then, yeah, just one last thing. Of course, we just need an output at the end, dp of 1 and equal to, which represents what's the minimum cost to get the root node to be equal to m. Right. Cool. Now let's go ahead and think about how we can optimize this dp. Well, one thing to note is for our value of m, we kind of don't care about the exact value of m. We just care about like what bucket it falls into for each node. So as an example, for the value of m equals 55, we've already computed our answer. And suppose I now change m to be 51. Well, I'm going to claim that the answer is going to be the exact same because this value of 51 here, it's the exact same as 55 because for every single node, it falls into the same bucket. Like 51 is bigger than all the nodes, just like 55 was bigger than all the nodes. So for something like this, we can just completely reuse our previous calculation of m equals 55. Let's do a slightly less obvious case. Suppose I change the value of m from 55 to just 45. All right, so now let's think about our DP table and which cells are still correct. Well, I'm going to claim that this cell is still going to have the same DP value because the element here used to be a 20. And like we've already computed the answer for 55. And if we now change it to 45, the answer still stays the same, right? It's the same cost to make it less than or equal to m, and greater than or equal to m. Similarly, this cell stays the exact same, so there's no need to like update that cell either. So basically, all we need to do is we need to recompute this cell. But after we recompute this cell, this is also going to impact all its ancestors. Because remember, this node's answers depended on the DP values of the two children. So to be safe, let's just go ahead and recalculate this as well. And then we'll also recalculate this. Because again, the root node also depended on this, the left child and the right child. And here, the left child might have been updated. So we'll just recalculate it as well. And so we can do some approach like this. And let's reanalyze our runtime. So basically, now we want to start by sorting m. So we start by sorting all of our queries by m. And then as our value of m changes, each node, if you think about each node, it's only going to need to be recomputed twice. Or like the chain of recomputes only need to start from it twice. So initially, you can just have m is equal to negative infinity, for example. And what this means is all your nodes are currently greater than or equal to m. And then as you loop through your queries, since you're sorting by m is going to be increasing. So at some point, so basically we have like 3 buckets, greater than or equal to m, equal to m, and less than or equal to m. And at some point, so for every node, they start at this bucket to the right, where it's currently greater than or equal to m for free. And then at some point, it might shift into it's now exactly equal to m. And finally, at some point, it might shift to it's going to be less than or equal to m. But we know this will happen at most twice. And so the number of times we need to start a chain of recomputes from any given node is bounded by 2. And when we recompute a specific node, we also want to recompute all its parent values. But because we have a heap here, the number of parents is only log of n. So the total number of recomputes we need to do is bounded by n times log n. And therefore, what we can do is we can first compute our DP like we discussed, assuming the value of m is negative infinity. Then we loop through our values of m in increasing order. And we just look at which nodes shifted buckets. And for all the nodes that change buckets, we start a chain of recomputes from that node upwards. And then, finally, that will give us the correct DP value at every single n. And our total number of recomputes is only n log n. So our final runtime is just of n log n plus q. Or I guess technically q log q, because you're sorting on your queries too. Okay. I guess any questions before we move on to the next problem? All right. Then let's go ahead and talk about our second problem, reachable pairs. So in this problem, we're given a undirected graph and also some operations. So the first type of operation is if s of t is equal to 0, then that node is just completely removed from the graph. And then if s of t is equal to 1, then that means the node is removed from the graph, but the connectivity of the graph is not affected. Because before you remove the node, you're going to add edges between all pairs of neighbors that the current node has. So let's do an example. And then what we want to do is we want to output right before each removal the number of pairs of nodes that can reach each other. Okay, so let's start by just like simulating this kind of naively with our sample here. So for our sample graph, we have nodes 1, 2, 3. And initially, they're all connected. So our answer is 3 because there's 3 pairs of nodes that can visit each other. And then what happens after we remove the node 1? Well, we remove the node 1, but 2 and 3 can still reach each other because it's the s of t here is 1. So before we remove node 1, we add an edge from 2 to 3. And so after this removal is done, our answer is now just 1 because there's only 1 pair of nodes that can reach each other. Okay, so if we could naively simulate this, then to count the number of pairs of neighbors or the number of pairs of nodes that can reach each other, to find that, we just need to keep track of all of our connected component sizes. So for example, if I have some connected component here of size 7 and another connected component here of size 3, then my total answer, we can do some math to figure this out. So this will just be like 3 times 2 over 2 is 3. And then this would just be 7 times 6 over 2, which is equal to 24. And then so we can just say our answer here will be 24. And then let's say I break apart this component. So instead of a size 7 component, it now gets broken apart into a size 3 and a size 3 component. Then to properly maintain our answer, we can just do what our old answer was, which is 24. And then subtract by the 7, the component of size 7. So minus 21. And then now we want to add in the 2 components of size 3. So we can then plus 3 and plus 3. And this new value will just be 9. Right? And 9 is correct for if you just have 3 components of size 3. Okay, so yeah, so it's not too bad if we could simulate the whole process, but of course we can't. So let's go over some subtasks here. So for our first subtask, we can just naively simulate it and our current algorithm would just work. Like after each update, you just do what the problem asks you to do and count the size of all your connected components. Let's do the more interesting one here where all of s of I is equal to 0, which means whenever you remove a node, it's just gone and you don't add any new edges. So this is actually a pretty classic problem, I suppose, for DSUs, where it's like, well, we start with some graph and then we want to delete nodes from this graph. And at each time we want to know like the number of connected components and all their sizes and do some math on that, right? So instead of breaking apart the graph, you can just do everything in reverse. So you just add nodes into the graph. Yeah, so for example, let's go through our second sample where all the updates are just zeros. So initially we have no nodes, and then what happens is we just add in node 3, and then we add in node 2, or I guess to be exact, you start by having the full graph, and then you just toggle on the nodes. So you start by toggling the node 3, then you toggle node 2, and then you toggle node 1. And when you toggle node 1, you loop through all its edges, and you merge it with 2 and you merge it with 3. And along the way, you can do some math to keep track of the answer. And so the answer is 0, 0, and then 3. So not too bad if we just have all the s of I equals to 0. Okay, let's do our second case, which is what if all of our s of i's are equal to 1? Well, it turns out for this, we can just simulate the problem like going forwards. So what this means is whenever you remove a node, the connectivity of your graph doesn't change, right? So let's do a slightly more non-trivial example. Suppose your graph looks like this. Like what happens after you remove this node, but you do it with operation 1? Well, technically you would first add in a bunch of edges like this pair of edge, this edge, or sorry, this edge, and this edge. And then you get rid of all these edges in the middle. But in terms of connectivity, it's the exact same as if you just didn't remove anything. Yeah. And so what we can do is we can just start with the original graph and you just keep track of the connected components in the original graph. And then whenever you delete a node of type 1, you can just decrement the number of elements in that component, right? So initially this has 1, 2, 3, like 6, this has 3. If I delete this node with type 1, then all that happens is I change this from 6 to 5. If I delete this node, then I just change this from 3 to 2. And then if I delete this node, I just change this from 2 to 1. And along the way, we can like update our answer in node 1 as well. Okay, cool. So that solves our case, our subtask where all the s of i's are equal to 1. And so now let's try to piece both of these together. So how can we try to do both operations? Let's do some example. Yeah, so let me draw an example here. So suppose you have some nodes that look like this, or a graph that looks like this. Okay. And of course, it doesn't have to be a tree. Yeah, but I'll just draw a tree for now. So let's suppose what happens is you have node 1, node 2, node 3, node 4, node 5, node 6. Yeah. Or I'll just make this 5 and 6. Okay, cool. And let's say I'll circle the ones that are operation 1 in blue, and then the rest are operation 0. So basically this means you're going to remove 1, but before you remove 1, you add like edges. And same thing for 2. Before you remove 2, you add the edges, then you remove 2. And then when you delete like 3, 4, 5, 6, you just delete the nodes. Okay, so now let's try to go backwards. And this is a bit trickier now, because if we try to go backwards and add in nodes, well, the first iteration is kind of simple. You just add in node 6 and you call it a day, right? But when you add in node 5, you need to somehow know that like nodes 5 and 6 are already connected to each other. And the reason why they're already connected to each other is because if you like simulate this process going forwards, then what would happen is when you deleted node 1, you connected 2 with 5, 5 with 4, 2 with 4. And then when you deleted node 2, you would have then connected 6 with 5 and also 6 with 4, right? Before you delete node 2. So at this point in our graph, after deleting 1, 2, 3, 4, and then, yeah, after deleting 1, 2, 3, 4, the nodes 5 and 6 are actually connected to each other. And so when we simulate everything in reverse and we add in node 6 and then we add in node 5, we also need to make sure that after you add in node 5, it's already connected with node 6. I think there's probably multiple ways of doing this, but one way is what you can do is you can just go ahead and keep all the nodes that are going to be removed with type 1 in the graph forever. Again, the reasoning behind this is just whenever you delete a node of type 1, you don't change the connectivity of the graph. So let's just leave the nodes in, and that will preserve our connectivity information.
Okay, so I'm just gonna leave, yeah, so I'll go down here and I'll just leave 1 and 2 in the graph or in the graph wrapper. And so now when I add in node 5 into the graph, I will just connect it with node 1. And then when I add node 6 in the graph, I'll connect it with node 2. And here, you have a connected component where 5 and 6 are connected to each other. But the size of the component is only 2 because node 1 and 2 don't exist yet. Yeah, so essentially what you can do is you just start by going from like left to right. And for each node that's going to be removed with type 1, you just connect it with everyone else. And then when you go backwards on your graph, yeah, so then when you go backwards, you're just toggling on nodes and saying that, okay, now this node exists, right? So let me just, I guess, illustrate this point one more time. So like 1 and 2 are already in a connected component in terms of like your DSU. And then when you add in node 6, you toggle node 6 to be on, and you also connect it to 2. So now the DSU component contains 1, 2, and 6. And then when you add in node 5, you also toggle it to be on, and you connect it to node 1. So now the DSU component contains 6, 2, 1, 5. And now the size of this DSU component is only 2 because you want to track the number of like toggled on nodes in the component. Cool. And then afterwards, you can like add in 4, which will put it in the component as well. And then you can add in 3, which will also put in the component. And then finally, what you can do for nodes that were removed with type 1 is when you go to toggle it on, the only thing you need to do is toggle it on. So like you just toggle node 2 on, and you don't need to connect it to anyone else because it's already been connected. But it doesn't like hurt if you do it again either. Yeah, so to summarize, you can basically just go from left to right and simulate and just connect all the nodes that will be removed eventually using type 1 to everyone else. And then now you can go from left to right and add in all the nodes one by one. And then whenever you add a node that was removed with type 0, you connect it to all its adjacent nodes. And then whenever you add in a node that was removed with type 1, you just toggle it on and increment the count of its component. And then as you're like keeping track of all your like connected components, you also want to track how each connected component size affects the answer. So essentially, whenever you merge two components together, if this was A and B, and this is now C, you first subtract A times A minus 1 over 2 from the answer, and you subtract B times B minus 1 over 2 from the answer. And then you add in C times C minus 1 over 2 into your answer. And then similarly, whenever you increment, you can just subtract the old value of A and then increment it by 1 and then add in the new value of A. Yeah, and that's pretty much it for problem 2. Any questions for this one before we move on? What would be the time complexity? Okay. Yeah, so first we did, if you don't do offline queries, I mean, like if you actually just simulate the process, it's probably like n cubed. Because worst case, after every operation, you need to like connect all pairs of nodes. But our current approach from the left to right case, you're just looping through all nodes and all edges at most once and connecting them in a DSU. And then similarly, when you're going backwards, you're also just looping through all the nodes once and connecting them with a DSU. And then maintaining the answer is always just some O1 operation with some math. So I guess amortize would just be like, oh, m plus m. And then technically, you multiply by the inverse acrobate of n plus m.
I have a question. What was the thing about like having two adjacent nodes with a value of 1? Like, why is that important?
So this matters because when we try to simulate adding nodes backwards, after we add node 6 and we add node 5, we need to somehow know they're already part of the same component, right? Like they're already connected to each other. No matter how many how many nodes are in between them in the original graph. As long as the original nodes in the graph are of type 1 or are going to be removed by the type 1 operation. Because whenever you do removals on these nodes, it doesn't change the connectivity of the graph, right? So that's why we just start by throwing them all into a DSU like together. And so when we go backwards now, we already have a component of 1 and 2 connected to each other. And then we can add in node 6, which will expand our component here. And then when we add in node 5 to node 1, that'll connect it to node 6 automatically.
So then when you first process things in order, if the current value is a 1, then you just merge it to everything, to all of its neighbors?
Yeah, if they're also 1s.
Oh, only if they're also 1s?
Yeah, because the other nodes, because you can think of it as like node, like all the 1s always exist in the graph, and then the 0s get added in backwards order. So on our first pre-processing step, we just connect all the 1s to other 1s.
Oh, okay. So then first you like go forward and connect all 1s to 1s, and then when you go back, you just add everything adjacent to each other, and then you just check the number of um, on nodes in its connected component,
Yeah. Mhm.
and that just works.
Let's go over our next problem here. Yeah, so our third problem is photo op. I think it's a well-named problem for operations, of course. Okay, so for this problem, we are given a kind of weird statement, but essentially, let's just draw like a quick Cartesian plane here. We have some value of x and we have some value of y. And this is where Bessie starts, and Bessie wants to get to y. So initially, the best path is, of course, to just take a straight line there. But then what happens is there's going to be like a bunch of other lines that she can't cross over. So for example, a line might look like this, and she's not allowed to cross over this line. So in this case, our best path is, well, we can either go here first and then go to here, or we can go here first and then go to here. And then I'm going to be drawing my arrows like not straight, but just assume that whenever you go from a point to another point, you always take the straight line path there. Okay, cool. And we have a bunch of these. So the number of like lines that can obstruct you is up to 10 to the power 5. And then they're also given in a slightly weird query fashion, but basically you have your obstructions. Okay, yeah, that's unfortunate. Okay, yeah, so for your obstructions, they have some time t, and that's the first time they become active. And what you need to do is you need to output the answer, which is the minimum distance from x to y, with those obstructions in for each value of t. Starting at 0, there's no obstructions, and then you go to t equals 1, and then everything that has t less than or equal to 1 will be added in as obstruction, and so on and so forth. Okay, so to be honest, I'm not too sure what like most of these partials are supposed to be. I guess for like n up to 100, you can just do some very brute force thing. Like you can model it as a graph, and then you just put edges between like endpoints. So you model every endpoint as like a node, and then you can put an edge between endpoints if you can go from one to the other without crossing any obstructions. And you can just do a very naive like obstruction check by doing intersections of lines. And then once you have that graph, you then just run Dijkstra's and find your answer from x to y, maybe something like that. But yeah, that solution will only get the endless up to 100 case. For the next two, let's just clump them together, because basically a O of n times t solution will get both, right? So here T is capped to be n, n+1. So yeah, this is like n squared, and this is nt, where T is only up to 10. Cool. So let's go ahead and reason about like how we can do a path, like what an optimal path might look like. And the claim here is we're going to start at our initial value of x, and then I'm going to go to some other value of x. Maybe I'll just call this xi. And then I'm going to go to some x or yj, and then I'll go to my destination value of y. And I might skip some steps in between, but basically my optimal path will always look like this. And let's just think about why this may or may not be true. So is it ever optimal to add in any like extra points in here? Well, there's a few ways you can try to add extra points. Like I could make multiple stops at different x's, for example. So I start my trip here, and then I make a stop to this value of x, and then I make another stop to this value of x. Well, that's unnecessary because I can just jump directly to here. Okay, so then what about I go to some value of x, and I go to some different value of y, and then now the question is, would I ever want to go back to like x and then back to y? And it's pretty clear that the answer is always no, because once you're at some y value, you can just go directly to y. And it's never better to go back down to y equals 0 and then go back up, right? No matter what your difference in x is. So yeah, our path is relatively simple. So start from your starting value of x, pick some x of I to go to, and then pick some y of j to go to, and then finally go to the destination y. And among all possible paths that look like this, you just want to find out which one's the shortest, right? And then finally, the only constraint is, well, if you look at this part, this path is always valid, and this path is always valid. So essentially, you just want to find the minimum like valid, or among all the valid xi to yj's, you want to find the one that minimizes this length, right? Okay. So I'll present one way you can do this in O of n times t, although again, I'm sure there's probably other ways. Let me just restart this. So again, let's just suppose we have our initial value of x here, and then there's a bunch of other x, like different values of x we can go to. And then there's also a bunch of like y values you can go to. But let's say this is the destination y value we want. Cool. So of course, for this value of x, if you can go directly to the value of y that we want, that's just your optimal path, right? But let's consider some cases where it's blocked off. So there's basically just two ways you can block off this path. You can either have something to the left of you go higher than y. So this would block it off. And the only other way to block it off is if you have something to the right of you go lower in y. So again, this would also block it off. Yeah, and those are essentially the only two cases. So we can go ahead and consider for our current value of x, we see, oh, we can't just go directly to this value of y that we want to. We can instead query which values of y I can go to. And so this will just depend on two things. So let's do it with just this line first. So suppose I have this line to the right of me that's blocking me here, right? Then that means I have to stay under this line. So my valid range of y values is going to be here or lower. And similarly, if you have a line to the left of you, maybe this line goes like here, then that's going to give you a range of positions of y you can go to or higher, right? So in this case, if we look at our starting point x here, you can go to here, that's okay. You can go to here, that's okay. But you can't go any higher than this because that's blocked off by this, this blocker. And you can't go any lower than this because that's blocked off by this blocker, right? Because you try to go here, that intersect. Cool. So that's effectively all. Like you can just query for every single point of x, you can figure out what's the smallest element to the right of you and what's the biggest element to the left of you. and that dictates your upper and lower bound for y values you can go to. Once you have a fixed upper and lower bound of y values you can go to, you can then do a bit of casework. So let's say this is my fixed range of upper bound and lower bound. So I can go to any y value in here. Well, first of all, if the y value is in that range, then we just go directly there and we call it a day. So what if it's not in that range? Well, there's only two possibilities. It's either above this range, like we might have something like this. So if our valid range of y's is here, then the value of y is above it, then you would want to go to the largest value of y you can go to, and then go to your destination, right? And then our final case is just if your range of y's you can go to is, if the destination y is below the range of y's you can go to, then you just go to the the lowest one you can, and then you walk down to y, right? So yeah, that's it. You just query this for every single point, and then check which case it is. Oh, and then I guess the final case is if you have an invalid range. So for example, if you have a blocker that looks like this, then you can't go anywhere. Then you can just skip this value of x. Yeah, and so you have n different values of x to try. Each one you can try it in O of 1, because you can do a prefix max and also a suffix min array. Yeah, so once you have a prefix max array and a suffix min array, you can easily query what's the biggest element to the left of me, what's the biggest element to the right of me. And then do your casework on where is my range of valid y's compared to where is the actual y destination we want, and just greedily figure out the answer in total O of n time. And then we run this same exact algorithm for each value of t, and we get O of n times t for our partials. Cool. Any questions on this so far? In fact, you actually don't care about the y value at index I when checking an x value. I feel like my solution does care, because like for each value of x, you compute the range of x's or y's you can go to. And then depending on where the real y is, you then know if you can go directly there or if you should go to the lowest point or highest point. But yeah, I'm sure there's other ways you can do this as well in O of n times t. Okay, yeah. When you do prefix min and prefix max and suffix min, you don't care about the y value at the current position. That's right. That's right. Yeah, that's right. So yeah, so at the current value of x, you only care about everything to the left of you and everything to the right of you, not the current. Yeah, so O of n times t is like not that bad. For the full solution, okay, let's go over that now. Cool. So for our full solution, essentially what we're going to do is we're going to maintain the optimal answer as we add each line into our each like obstruction into our graph, let's say. So you can start by just adding a bunch of obstructions, and then of course if they never cross your this line's just your best answer, right? So like you add a bunch of obstructions here, 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 and then maybe even more obstructions here, 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 like who cares, right? Okay, so then I guess the main thing we care about is whenever like a line segment actually intersects with your value, with your best line currently, how do you then find your next best line? All right, so for now, bear with me. We're gonna forget about our initial line, and we're just gonna think about obstructions in general. So suppose you have one obstruction line that looks like this, and another obstruction line that looks like this, and another obstruction line that looks like this. So this is like a pretty complicated mess, right? And then pathing around here is kind of tricky. But it turns out you can view this as a solid quadrilateral. You can just think about this as if this whole thing was filled. Yeah, and so let's just consider some paths you can take, right? And let me unfill it in. So let's suppose my current value of x is here. Well, I can walk to here, walk up to here, and then go up or down. And so that's the exact same as if it was this like fully filled quadrilateral, right? And then similarly, I can walk to here and then go like under or something like that. But like I can't really go in the middle and then try to go anywhere, right? Like going in the middle here is just doomed. So this, whenever you have like lines that intersect, you can just view it as a like fully solid rectangular piece or quadrilateral piece. And for your quadrilaterals, they can be defined by a few things. So for your quadrilateral, you just care about 4 points. What's the lowest y value, which we can denote as y1? What's the highest y value, which we can denote as y2? What's the lowest x, x1, or smallest x, x1? And the biggest x, x2. And yeah, so if you have these 4 points, that like properly defines your quadrilateral. Cool. And so let's just think about one quadrilateral for now. So if you got this quadrilateral, there's only a few paths you can really take around it that make sense. Right. So let's say my value of x is to the right of the quadrilateral. Then the only path that we would ever want to take is you go to x2, and then you go up to y2, and then you go either up or down to your actual value of y, right? Okay. The other path is you might want to go to x1, and then you go to y1, and then you go up or down to the actual value of y. And so essentially these are the only two paths, in fact, no matter where your x is. So if your x is to the right, then your paths look like this. If your x was in like the middle here, your paths are still the same. You first go from x2, or you first go to x2, then you go to y2, then you go up or down, or you go to x1 first, then you go to y1, and then you go up or down, right? So regardless, for a single quadrilateral, your path always goes from x to x1 to y1 to y, or x to x2 to y2 to y. What if there's a line from x2 to y2? Yeah, that's okay. It doesn't affect anything, right? Like, it doesn't matter if your lines are in the middle here, like we have like this, or if there was a line actually like this, because from x2, regardless, you can go to y2. Yeah. Because even for your previous solution, like if you're at a current value of x, you don't care about this line, right? You can still go like above or below it. Yeah, so it's the same thing here. Cool. So that's the main observation. And so just considering a single quadrilateral, yeah, you're going onto it, and that's okay. Yeah, like you're allowed to go like on the path essentially. Okay, so for a single quadrilateral, these are your only two valid paths. Cool. So now let's consider like two quadrilaterals together. So this case is kind of trickier to think about, but let's do it. So let's say here's my first quadrilateral, and I'll just draw them as like something like this. And again, here we have, let's call this AX1, AX2, AY1, AY2. And then let me have a second one here. Okay. So let's say this is BX1, BX2, BY1, BY2. Okay, let's consider all the paths we can take going from like one to the other. So it turns out there's actually just two. We'll talk about merging and stuff later. Yeah. So for now, let's just consider there's like two disjoint quadrilaterals, one on the left, one on the right. And let's think about all the paths we can do. Okay, so we start from some x, and we already have this path mapped out, and we already have this path mapped out. So we don't need to worry about that. And similarly, we already have like this path and this path done from the quadrilaterals themselves. So what other paths might we want to take that the current quadrilateral paths don't include? Well, one thing is, what if here's my value of x, and then I first go to ax2, and then I go up to by1, and then I go to y. So this could be a better path that the current paths don't include. So let's go ahead and write this out. So x2 ax2 to by1 to y. And then similarly, you might want to go from some value of x to bx1 to ay2, and then to y. Yeah, so because basically this first path is basically like an optimized version of you go from x to here to here to here, right? And the reason why it's more optimized is because this section is longer than if you just went directly here and then up to y. So essentially, yeah, you might want to try the paths where you go to the adjacent corners. And then similarly, the second path is more optimal if you're trying to reach some y that's like down here. So it's more optimal to go to here and then here. So you're basically cutting this corner instead of going up here and then down, right? Okay, so these are the two additional paths you want to consider. And then you also have like an edge case here, which is a little annoying, but let me just write this out real quick. Oh, okay, one second. That work. Kind of. Okay, I'm like struggling to get this to work. But essentially our edge case is if your value of y is in the middle here. So let's say this is your value of y, then instead of going to one of these paths, you can just like chop it short. So for example, you can go to x to ax2 to y directly, or you can go from x to bx1 to y directly. Yeah, so that's your edge case. So this is a case where you have like big y, like y is above. This is your edge case when y is below, and this when y is in between these two, then you go like this. There's actually no other edge cases. Okay. Yeah. So then for our actual like answer, essentially after we add each line, we add each line in as a rectangle. So initially you have some line xy, and you can just turn this into the rectangle xxyy. And then whenever you add or remove or like whenever you add or merge rectangles, you want to keep track of all the current valid paths. So you can do this with like do it with like a set of rectangles. Or I'm calling these rectangles, but like there's usually quadrilaterals. And then you also have a multi-set to store all the answers. Or paths, up to you, what you want to call it. So this stores all the paths, and then this stores the set of rectangles. Whenever you add a rectangle, so let's say you have like R1, R2, and then now you add in some new rectangle R. Well, first of all, you need to compute the two paths that go through R, so these two that we talked about, and add it into the set of possible paths. You also need to remove the two paths that R1 and R2 previously had because they were next to each other. So remove these two paths. And then you need to add in like two new ones, where you do the two paths from R1 and R, and also the two paths from R and R2, and add that into your paths. And then whenever a rectangle merges, so yeah, so let's say you have like rectangle 1, rectangle 2, rectangle 3, rectangle 4, and you merge R1 or R2 with R3. Then this rectangle no longer exists, so remove its two paths from path. This rectangle no longer exists, so remove its two paths from path. Merge them together, let's call this R5, and add the two paths of R5 into paths. And then similarly, you need to remove the two paths that used to exist because of R1, R2, and the two paths that used to exist because of R3, R4, and then add in the two new paths from R1, R5, and the two new paths from R4, R5. Yeah, but overall, your runtime is fine because your number of rectangles is bounded by n, and the total number of adds you do is n. The total number of merges you can do is also n. So your overall runtime is just O of like n log n. And then to query your answer, you basically just look at the minimum value in paths, because you're storing all the valid paths that are generated from each individual rectangle and pairs of adjacent rectangles. And then you just take the minimum path possible. And then finally, there's one last edge case here that you need to worry about, which is we've considered all these paths, but we haven't really considered just the path going from X to Y, for example. So after you updated all your rectangles, you then want to query for the first rectangle to the left of you and the first rectangle to the right of you. And here there's a few more cases where it's like, if you're in between two rectangles, then you can check if you can go directly to Y. If you can't, then you can check if you can go here to Y, and you also want to check if you can go here to Y. Yeah, so those are the three paths you need to check. And then another case is if you are like eaten by one of the rectangles, then it's slightly different. So here you want to check if you can go here to the previous point to Y, or from here to Y. Yeah, eaten or like contained in one of the quadrilaterals. Yeah, so this problem is like, I'm not sure if this is the intended solution. It like works, it runs in time, it gets the correct answer, but like the implementation is like pretty hard. Although like technically all you need to do is like maintain a set of rectangles and maintain another multi-set of like paths. Yeah. Any questions? Like there's definitely a lot of specifics that like you need to work out on paper in like each individual case. Oh, and sorry, one last thing for rectangle merging. This part's actually the easiest part, I think. So if you have rectangle 1 here, you just find an adjacent rectangle. The only way for them to not merge is if your x values don't overlap and your y values don't overlap. So you look at your y2, compare it against their y1. If they're not overlapping, that's fine. And the same thing here, you look at your x2 and compare it to their x1. And if they are not next to each other, or if they are like x2 followed by x1, then it's fine. So if it's this case, you don't intersect. If it's not this case, you intersect. And to intersect, you just take the min and max of like the x1s, or like min x1s, max x2s, min y1s, max y2s. And that's it for intersection. Yeah, that's it for intersection merging. And then every time you make a modification on your set, you need to make sure you properly update all the paths you have. Okay, cool. Yeah, that's all for the goal problems. And then probably wait for the editorial on this one to see if there's like a nicer approach. But like this way does work, so.
Okay. Thank you, Ybor, for hosting the Go section. So I guess that concludes our January live solution. Thank you everyone for participating. If you have any questions, feel free to post on Discord or on our YouTube channel. All right, everyone, have a good night.